Hello and welcome to problem set 20. Our problems today will be from the topic disaccharides and polysaccharides. Before we get started, just a quick reminder that the worksheet to accompany this video tutorial is available online through my website. And with that said, let's get started with problem number 1. Number 1. Label the following carbohydrates as monosaccharides, disaccharides, or polysaccharides. So we've got an A through H. A is glucose. Glucose is a monosaccharide. B, sucrose. Sucrose is a disaccharide composed of D-glucose linked to D-fructose, and they're connected by an alpha-1 beta-2 glycosidic bond. So two monosaccharides linked together makes it a disaccharide. C, amylose. Remember that amylose is a polysaccharide composed of D-glucose units connected by alpha-1,4 glycosidic bonds. So for amylose, you should write polysaccharide. D, maltose. Maltose is composed of two D-glucose units connected by an alpha-1,4 glycosidic bond. So two monosaccharides connect to make a disaccharide. E, fructose. Fructose is a structural isomer of glucose with the formula C6H12O6. It is a monosaccharide. F, glycogen. Glycogen is a polysaccharide composed of D-glucose units. They're connected by alpha-1,4 glycosidic bonds, and there are branching D-glucose units that are connected to that initial chain by alpha-1,6 glycosidic bonds. So glycogen is composed of many glucose units. It is a polysaccharide. Lactose is composed of D-galactose connected to D-glucose, and remember that they're connected by a beta-1,4 glycosidic bond. And because it's composed of two monosaccharides, lactose is a disaccharide. And last but not least, we have galactose. Galactose is one of the monosaccharides found in lactose. So galactose is a monosaccharide. Okay, so we're going to need quite a bit of room for number 2. So let's go ahead and erase here before we go on. Okay, number 2, cellobiose results from the breakdown of cellulose. Given the structure below for cellobiose, which I drew on the board as well, complete A through D. A, what are the monosaccharides that are linked together in cellobiose? So for part A, you may just remember it from the example that we gave in tutorial number 20 for an example of a disaccharide with a beta-1,4 glycosidic linkage. So you may already remember the answer to A, but just in case you don't remember it, we can take a look at the individual monosaccharides and the orientation of these OH groups, and we can see that they are glucose. Both of them, they're the same, and they are D-glucose molecules. So we have two D-glucose molecules in Cellobiose. Part B, circle and label any acetals, hemiacetals, and alcohols in the structure. Okay, so let's do this in all our different colors. So let's use the blue to circle any hemiacetals. Okay, so there is one. Remember that a hemiacetal is connected to both an OR and an OH. So we have a hemiacetal here. Now notice over here that the hemiacetal reacted to form the acetal linkage. So let's label the acetal in green just to make it stand out from the hemiacetal. So we have a carbon connected to an OR and another OR group. So carbon connected to two OR groups, that is an acetal. And last but not least, let's do our alcohols in red. Everything that's left over is just an alcohol. So I'll circle all of these OHs, all these hydroxyl groups. And let's draw a line over here. Oh boy, there's a lot of them. And write alcohol. Okay, and I'll just put a check mark here because we did that part in the drawing. All right, part C. Is the glycosidic bond oriented in the alpha or the beta direction? Okay, so remember that the glycosidic bond is what we call the acetal linkage in a sugar. In a sugar, it's always called a glycosidic bond. So we're asking, in part C, they're asking about the orientation of this bond right here. And because it is pointing up, which is the same direction as the CH2OH, we have a beta orientation. Okay. Part D. What type of linkage exists between the two monosaccharides in Cellobiose? Okay, so we already know that the acetal linkage is in the beta orientation, so we'll go ahead and rewrite that down here. And then if we look to see which carbons of the rings are connected in that glycosidic bond, we will find that it is the 1. So let me go ahead and label all of these, 3, 4, 5, 6, and it's connected to the 4. So again, I'll label these 1, 2, 3, 4, 5, 6. So it is a beta 1, 4 glycosidic bond. Okay. So that completes problem number 2. Let's go ahead and erase before we go on to number 3. Okay, number 3. Benedict's reagent was once used in hospitals to test for glucose in urine. Benedict's reagent contains copper 2 ions, which have a sky blue color. Upon reaction with a reducing agent, the copper 2 ions are reduced to copper 1, which forms a dark red precipitate of copper 1 oxide. Which of the following would you expect to act as a reducing agent in a reaction with Benedict's reagent. So in other words, which of the following would you expect to be oxidized? Circle all that apply. Okay, so A through D, I have drawn them out on the board to make this problem go a little bit faster. I am assuming that your instructor probably doesn't want you to be able to draw these from memory. Maybe they do, I could be wrong about that. So I'm assuming that you would probably look up these structures to do a homework problem like this. And your instructor maybe would give you the structures on an exam. Again, clarify with your instructor. So for A, is it a reducing sugar? Really what this question is asking is there a free hemiacetal? Because if there is a free hemiacetal, then we know that in solution, it would be undergoing mutarotation and converting between the alpha and the beta form. And in order to do that, it has to go through the acyclic form, which has a free aldehyde, and an aldehyde can be oxidized. And in being oxidized, it can cause the copper 2 ions to be reduced to copper 1, giving you a positive test with Benedict's reagent. Positive test for a reducing sugar. Okay, so let's look at maltose. And notice that it does have a free hemiacetal. Which means that it does have an aldehyde present in an aqueous solution, and that aldehyde can be oxidized. And so maltose can behave as a reducing agent. It will cause the copper 2 to be reduced to copper 1, and we will get a positive test with Benedict's reagent. So I'm going to write here for maltose that it is a reducing sugar, and it will give a positive test. With Benedict's reagent. All right, B, we have sucrose. Look at the structure of sucrose. There is no free hemiacetal. The reason is because the hemiacetal from the glucose reacted with the OH off of the hemiketal in fructose, producing this alpha 1 beta 2 glycosidic bond with no free hemiacetal for reaction. Okay, so it doesn't have a hemiacetal that's free to undergo that mutarotation in an aqueous solution. So no free aldehyde. Okay, so I'm going to write here, no free hemiacetal. So you'll get a negative test with Benedict's reagent, not a reducing sugar. Okay, see, so we're supposed to circle all that would react. So I should circle A, don't circle B. All right, C, we have galactose. Galactose has a free hemiacetal. So just like maltose, we would expect this free hemiacetal to be undergoing mutarotation in an aqueous solution, which means that in the acyclic form, it would have an aldehyde that can be oxidized, thereby causing the copper 2 ions to be reduced to copper 1 and giving that positive test as indicated with the color change from the blue to the red, forming the red precipitate. So circle C. C will give you a positive test. And last but not least, we have D, Cellobiose. Look at the structure here. We do have one free hemiacetal. Just one though. Notice that the hemiacetal of the other glucose unit reacted to form the acetal. The acetal is not free to undergo that mutarotation. So there is one free hemiacetal, therefore it can undergo that mutarotation at this position, forming the aldehyde in the acyclic form, and that aldehyde can be oxidized to give a positive test, so circle D. All right. Let's erase number 3 and go on to number 4. All right. Number 4, amylopectin and glycogen have very similar structures. Briefly explain how these two differ structurally. So amylopectin and glycogen, remember, they are both polysaccharides. And they're both composed of D-glucose units linked together by alpha-1,4 glycosidic bonds, with branching units coming off of the primary chain, and those branching units are linked by alpha-1,6 glycosidic bonds. So how do they differ? Remember that amylopectin has those branch groups coming off less frequently. About every 25 glucose units, you'll have a branch. Glycogen has those branch units more frequently, about 2 to 3 times more frequently. For every 8 to 12 glucose units, you're going to have a branch group coming off with that alpha-1,6 glycosidic bond. So it's right up here that both amylopectin and glycogen are polysaccharides composed of D-glucose units connected by alpha-1,4 glycosidic bonds. They both have branched chains of D-glucose connected by alpha-1,6 glycosidic bonds. In amylopectin, the branches occur less frequently at approximately every 25 glucose units. In glycogen, the branches occur more frequently at approximately every 8 to 12 glucose units. Okay, so the shortest answer is that glycogen is more highly branched than the amylopectin. All right, number 5. Which disaccharide is made up of D-galactose and D-glucose connected by a beta-1,4 glycosidic bond. I hope that you recognize that description as being the disaccharide lactose. So you should be able to give a description like what appears in number 5 for the 3 different common disaccharides that we talked about in tutorial number 20, as well as the 4 different polysaccharides that we discussed in tutorial 20. All right, number 6. What 2 monosaccharides form from the hydrolysis of sucrose? So knowing, again, that brief description of the structure of the disaccharide sucrose, you should be able to then tell what 2 monosaccharides would be formed when that acetal linkage, that glycosidic bond of sucrose, is split apart with water. Hydrolysis, remember, it means split apart with water. So sucrose is a disaccharide formed from D-glucose connected to D-fructose by an alpha-1 beta-2 glycosidic bond. So when that acetal linkage is hydrolyzed, the D-fructose and the D-glucose are liberated. So the product of hydrolysis of sucrose would be those 2 monosaccharides. So let me write down here. We would have D-glucose and D-fructose. Okay. So that will conclude our problem set number 20. I hope that this has helped you solidify your knowledge from tutorial 20, and I hope that you will consider tuning in to tutorial number 21. Thank you very much.